Let's get started. I think I'm going to start from the triple integral one, since it's, I think, the harder problem of the three. And what you see here, essentially what you're going to be doing is you're going to be intersecting a cone with a hemisphere. I don't know why they don't show the hemisphere here. Maybe if I haven't taken a screenshot of the hemisphere, it should be there. But basically you're bringing this bad boy, you bring this bad boy in and you make them intersect with their bottoms again here. Their bottoms are going to be on the XY plane. So what we're seeing here, again, this direction here will be the Z going up, okay? And then the XY plane would be here. So this helps again a little bit with the bounds later. That's Y and X. Okay, so we got the picture, right? And you may have seen that, first of all, you're given the equations of the cone and the hemisphere. The hemisphere is very predictable. It's like a big circle, like you know how we have x squared plus y squared in 2D? Now you have plus z squared equal to something. So that's typically, again, even if they don't tell you, you'll know that this is a sphere of some sort. This is a full sphere, but they're telling you you're going to take the top half of it, right? So this guy here is the equation of our sphere. And again, we're constrained by the XY plane. So that means, again, our Z value, one of the first things we need to note is that our Z needs to be greater than 0. Okay, so that's the sphere. And then the cone is that little square root function, which, you know what? We should, honestly, when you see it written like this, you probably want to match the forms of the two shapes because you'll want to find intersections, right? Eventually, you'll want to find intersections. And right now, this would be more easily pluggable into this one if they both agreed on what they look like. What I mean is, let me just move this around a bit. I would probably rearrange here. I would express everything in terms of Z squared. You know, just by looking at it by eye, I think this is best. So we would have here Z squared is equal to, let's write this as 8 squared. And then maybe minus x squared plus y squared. Something like that. Right? Like this guy here, these will move on the other side. It will become negative, right? And I'm just factoring the negative out. And then I'm noticing here this again. This guy is familiar. Could any of you tell me what this is? Like think cylindrical coordinates, because that's what we're working right now. What is this guy? Not any kind of R though. Like technically in math, they call this R rho. Don't mix this with density in EC 106, right? They call it rho because again, it's again, we got to distinguish the difference. Let me remind you one last time before your midterm. So in a cylindrical coordinate system, rho is this distance. You see from the z-axis, it goes like this or like that, like in this direction. That is very different than the R in the sphericals, right? Which again goes any way away from the origin. This guy here is R. You see the difference? Very different. Okay, so don't mix those two up. And you know, if you have to distinguish them by calling it rho, do so. Okay. Anyways, now that you recognized it though, we'll call it rho for now. Not in EC 106 though, just in Math 119. Okay, so we've got here that Z squared. We're in nice cylindrical coordinates now. We got that this is equal to 8 squared minus, well, this is rho squared, not just rho. There you go. And then the other guy over here, I wish to square his equation so I can get a Z squared. And I'm going to get it to be 3x squared plus 3y squared, but I can also factor again the 3's here. Why not? So I got Z squared is equal to 3x plus y squared. well, x squared plus y squared. And again, with the same coin, with the same token, that guy is again rho. We see it here. So this is basically just 3 times rho. Okay. And this again, now that I've put the equations down, I've got 2 of them.
Right. Is it rho squared?
Rho squared, yes. Yep. Sorry about that. So we got 2 equations here, Kelly and Olivia. And they're both talking about z squared. Now remember, again, we're trying to figure out our constraints. The goal is to find the volume between the intersecting region. So the intersecting region here, you can see it. I'll shade it in. It's this guy. We're trying to find, again, the volume of this. And it looks like an ice cream cone because, again, the top of the sphere here is basically the ice cream, and the cone, again, the yellow part is, you know, the cone of the ice cream. So we're trying to find out where they intersect. Now, if you can see here again, they both talk about z squared. I want to find the intersection. I really do. I wish to do exactly that. So obviously here I just set them equal. Okay. I try to find those intersection points. It's like the equivalent of what we did in 2D, you know, when we're doing these problems over here in the very beginning, you know, for example, here, right, we're trying to find like these points A, B, and C because they help, again, tell us the bounds, right? We're trying to find the same thing now, but in 3D for a triple integral by setting these guys equal to each other. So you get to set them equal, and you can see that you get a very simple expression now for what rho squared should be. So let's try and solve that. This here moves on the other side. It becomes 4 rho squared, right? And this is 8 squared. Okay. And if I go and divide now both sides, this is just 64 divided by 4, right? And that's it. That's all you have right now for your rho. So this is going to end up being 16, or, you know, if you square root that, let's be careful. So rho squared here will end up being 16. That is nothing more than 4 squared. I hope I haven't screwed up there my simple math, but the rho here, you know, you'd get plus or minus 2, but rho can't be negative. We said why, because it measures the distance from the z-axis. So this is just 4, right? And that, you know, now that is going to be one of your bounds. So in typical fashion and how I did things yesterday, I'm going to say that the outer bound right now for rho, okay, outer bound is going to be 4. Now, what's the inner bound? Well, for that, again, you need to take a look over here and decide how you're going to do the integration. So I'm thinking of doing the integration like this. Let me show you again visually, and whoever wants to jump in and help, be my guest. So I want to do it in terms of rho. So I'm going to start down here. This vector is supposed to be very small right now, like 0. So I'm going to start down here at the very bottom of the cone. What I'm going to do to this arrow is I'm going to be doing circles around again. And then once I'm done this part and I formed a disk, I'm going to go up. Let me just go where I have a little more space so I can show you that. So again, I'm going to start from rho equals 0. Just make a step and then go around. That will make a ring right now, okay, as I go around here. Very bad to show this on OneNote, but you probably get the point. I'm going to make a little ring of this kind. I want to show you again what I'm trying to do with the vector. This is what I'm drawing. And then I'm going to grow the vector a bit, right? I'm going to grow the vector a bit, rotate it around, make another ring, right? And you can see how slowly I'm going to build up a disk, right? As I'm integrating like this. Now, obviously here, what is phi doing? If I'm doing these rings, again, continuously to form a disk here, what is rho doing right now? Sorry, phi. What is phi doing?
0 to 2 pi.
Right, because we're always moving around, and the phi range is always from 0 to 2 pi. Again, that's easy to put, and because we have values for phi, I'd prefer again to put it on the bottom here right? Because I told you it probably is going to be our very outer integral. Could be the case, though, in this problem that all of the integrand bounds are constants. That would be nice, but sometimes they're not, right? And I'm in preparation here. I see two constants for this guy. I'll leave them outside, because it's probably the very outside integral. Then I have rho over here. And again, don't forget I'm in cylindrical, so I have to deal with Z as well. Okay, so the idea is that I'm walking this vector again and repeating the process, right? I'm doing this again and again until I reach the intersection point, right? Like I'm gonna get up here, like I'm gonna go like this again, and eventually I will reach the intersection point, right? I'm gonna go over here. That's it, right? So we want to figure out right now, we want to figure out how long did that take, right? In terms of Z and in terms of R. Well, the R again is very obvious. You have a choice. I should be careful to tell you. You have a choice to run your integrand in the Z direction, to run your integral in the Z direction, or to run your integral in the R direction. And it's kind of like how yesterday I was switching the order of dx and dy, right? You have the same freedom here, which means, okay, you got to figure out very carefully what the bounds are going to be for this cone. Now, I know that the limit up there, what did I find out? What was this rho up here? We just worked that out. What was this to the intersection of the two? How much was I from the z-axis? You remember?
4.
4, right? So I actually do have that. I have that 4 up there. And you can see again that I start from the 0. Now, for the sake of simplicity, I'll choose those to be my bounds for rho, okay? I'm going to go here from 0 all the way to 4. And again, these are constants, which to me suggests that the z might not be a constant. So I'll put the z first to happen over here. I don't know what the z's going to be right now, but we're doing a volume integral, and I need all 3 bounds here. How do I figure out the z, though? So for the z, okay, I want you to remember, this is now going to trigger some EC 106 memories, that this guy is related to this guy, okay? Also, I want to make sure we understand that we could do this integral in spherical coordinates too. It's up to you, like what you decide to work it in. If you do it in cylindrical, okay, you use the cylindrical volume element. If you do it in sphericals, you use the spherical one and fill in the appropriate values for the bounds. So for example, if we were doing spherical, these would be r, phi, and theta. I decided to do it in cylindrical, so it's z, rho, and phi. But in any case, you would be able to get all of these variables if you know, whatever coordinate system you choose right now. So I'm taking a look over there. That's 4. Okay. And I think I know one more side here. Okay. I think I know one more side. And I'm going to bet that you know this side over here. Can you think about what this side is that I'm drawing? Goes from the center of the hemisphere, and the intersection happens at the surface of the hemisphere. So what could this be? Do you have it?
Like the maximum value of R?
The maximum value of R. So the radius of the hemisphere, which again, over here, you can obtain from the equation, Olivia, okay? It's not 64, don't let that trick you, because this is r squared here. Like on the equation of the sphere, this is always r squared. So whatever is here, you gotta square root it to get the radius. So we know that that radius is 8 right now, okay? It's in the equation secretly. So with that being said, you can see that we form a right angle triangle now in there. And how could I get the last distance here, the maximum z value, for example? Oh, one more thing, hold on. I think I think that's not what they're asking. One second. I feel that they want to find the entire, so the ice cream cone given by the region bounded between the two surfaces and the top half of the sphere. I feel, girls, that they're not asking about, so it's a debate here. Are they asking about this volume right here? Or are they including this bit over here? I feel that they're including that bit over there because the top, like if you take this away, I don't know about you, but it doesn't look like an ice cream to me. You know what I mean? I'm just judging it subjectively right now because they haven't provided a diagram or anything like that. So I don't know if you agree with me, but I think if you take the top one away, this just looks like a cone. This is a cone, right? It's not an ice cream cone. You know what I mean? So I'm just judging it subjectively. Now, if that's the case, cylindricals may not be the best way to go, okay? Because I could do this integration very easily on sphericals. If we include the curvy part, we need a variable that's curvy, if you know what I mean. Like if we're curvy, we need a variable that's curvy. And Z's not curvy, rho's not curvy. Phi is, but phi takes care of this direction, right? It doesn't take care of that direction. Who takes care of this direction in sphericals right now? Like, who is really this guy right here? Who's this guy in sphericals? Do we know? The angle, yeah? Kelly?
Theta.
Theta. So that's the polar angle. And I could tell my integral right now what this polar angle is as I integrate. So I'm switching you a little bit from cylindricals to sphericals because I realize that the goal is to include this, okay? And in cylindricals, that's not an easy task to do. None of the information that we have changes though. This is still 4, this is still 8, right? We're good to go with that. But the only thing that's different right now, I need to change, of course, the variables that I have in the integral. Okay, what is this angle theta right now? The way we see it, could any of you tell me? How could you use this information to get theta? What is theta?
Sine of 4/8.
Yeah. I believe this is the 30-degree angle, right? That's sine inverse of 1/2. I'm pretty sure that's 30. Wait a minute. Just to verify. So 30, 60, 90. And again, that's 1, √3, and 2. So sine inverse of 1/2 is the 30. Okay. So pi over 6. Cool. So that's the extent that theta is going to go. Now, if you're imagining the integration happening in spherical coordinates, how do things change? I'll tell you how they change. So let's draw our r vector right now, see what it does. So we start the integral, let's say from up here, theta is equal to 0 right now. And what we do is we do a ring like that again, from 0 to 2 pi and phi. That phi bound has not changed. And then we open up again over here. What theta does, you start like this, making a small ring, and then you go and grow it, right? And as you grow the size of the rings, the value of theta is growing. I don't know if you can see the vector, how it becomes more and more distant from the z-axis as you grow the actual rings. And then you reach, of course, the maximum, the bound here, the pi over 6, right? And that's where your theta is going to stop. So that's going to stop you right there at pi over 6. And then you go down a bit, boom, and repeat the same process. Ring again, small one here, grow, 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 all the way up to the maximum theta. So you've already figured out 2 bounds for theta and for phi. So I'm going to discard our work over here because this is not applicable anymore. So we have for theta, we start at 0 and we end up at pi over 6. For phi, we start at 0 and we end at 2 pi. So the question is then, what are we doing with our r? that could potentially host a variable here. What are we doing with this guy to complete the integral? Well, to answer that, again, we need to see what the relationship is between the two, okay? What is the relationship between r and theta right now? And we can probably see over here, let's say, if I am hanging out over here on a particular ring, let's say, of the integration, some particular ring that I was working on to do the integration. And I want to find out what this r is, okay? The way I could do it, the way I could think about it right now, I could use this information here, right? I could use this side, and I could use that side, the remainder here, and I could figure it out. That's what I'm thinking, right? So I just want to know what r does. Now, you know, if you're in sphericals at the moment and you're working this out, the value of r, okay, I'm going to make it visual for you. I changed my mind. I'm going to make it visual. Can I ask Olivia, take a look at my vector. And all I want you to do, Olivia, as I do the integral the way I described, I just want you to tell me, what do you observe for the length of this vector? How much does it span, okay? So I'm doing the integral the way I described to you. Look where I'm starting. Look where I'm starting. This is infinitesimal down here. I can't make it smaller. And just tell me what it does as I fill in the ice cream cone. How big can it get?
The maximum that it will span would be the. Actually, like, does it go all the way to the top, including like the little circle at the very top? So it would be the radius, which we found to be r, which we found to be 8.
So, you know, your r vector here, you're going to tell me, isn't there, like, what about the cone? Doesn't it, like, constrain r? You know, shouldn't we worry about a function? We have already, like, your r is constrained from the theta bounds. Like, it's only working. It could have been doing this, right? Going around the entire sphere, but we've constrained your r between pi over 6 on both sides here. Okay, we've constrained it. So there's no need for the function of the cone to come in place. The constraint here of theta is enough, right? Pi over 6 to keep this guy in check. So he doesn't go and visit every single theta available, right? He's only able to visit these thetas here. He cannot go further than that, right? And then as for phi goes from 0 to 2 pi. And as for his size now, for the r vector, it can stem again from 0 all the way to the radius, as we do the last bit over here, right? That's what it does. So no need again for a complicated function, constant bounds. We go over here and we say we go from 0 to capital R. And this is beautiful now because the volume is simply this. Do you remember it in spherical coordinates? You might have to. You remember what this is?
Is it RD theta?
Don't forget the square and the sign, and then all of the variables.
Oh, okay, yeah.
Let's just write them down. So it's a triple integral, of course, and the bounds are all constants now, which is nice. I don't have to integrate crazy stuff. So we put them in. Okay, the hard part is always the integrand. It's never going to be the actual. I don't think the integral is going to be the problem ever. I think the integrand is always going to be messed up. So we put them all in, and this is what you have. And now you can just evaluate, right? So you can split these apart if you so desire, right? Because they don't have any variable dependencies. You can split them apart, okay? And solve. Okay, that's all that remains here. So very easy, very easy integral to do right now. You got here from the first one, r cubed over 3. You got from the second one, 2 pi. And from the third one, again, you'll have to evaluate it. It's going to be negative cos, evaluated between these values. But because we have the negative, I might just absorb it in the bounds and write it as pi over 6 to 0 instead to take care of the negative. And then we have 2 pi r cubed over 3. And then we have cos of 0 minus cos of pi over 6. Cos of 0, of course, being 1. And cos of pi over 6, we got the actual guy over here. Pi over 6 is 30. So you get root 3 over 2, adjacent over hypotenuse. So that's what you got there. And that's your volume once you get it all down. Okay. So not a big deal.
Wait, sorry.
Yes.
Why do we put capital R instead of 8?
Instead of?
8.
I haven't filled it in yet. I should have filled that in. But this is 8. But it's the radius of the sphere, right? It's tempting to do that, Kelly, because I'll tell you why. Because we do that in EC 106 all the time. We just write this as r cubed, and I just forget that it has value here in math. It has a value. So that would be the volume. You're correct, right? We have to replace that with 8. You get that again from the equation of the sphere. That's it, right? So again, I showed you that we started here thinking about it in cylindricals, but we realized that, describing this part, I'd have to split the integral for cylindricals into 2 bits, and the top bit here wouldn't be very friendly. So I go, can't I do it in sphericals? Because, in sphericals, we have this nice variable theta that does the curviness here for us, right? And our r vector does this, and our phi does this. So we can fill this space up with spherical coordinates much, much more easily and more readily, right? So that's what we did. Now, don't forget what else was needed as well, right? We had to be clever and get some information from the equations, namely the intersection points by setting the equations again equal, right? We had to find a clever way to set them equal and find where they intersect. And another thing we had to get was the bound for, theta. So to get the bound for theta, I had to look at my diagram, right? Because I had a right angle geometry here, and it was really easy to set it up once I saw it. Once I got those down, okay, so I had these two now. I just asked, how much does my r vary? And I got that from the equation of the sphere. I knew the radius of the sphere is 8. And from my diagram, I can see mentally that my r goes from 0 to 8 all the way to the radius when I fill this space up, right? So that's how we did it. And another example here of, I guess, a triple integral. So this is a moderate example. I think the one we did yesterday is a lot harder. And then there's the easy one, which is the volume between 2 spheres, which is the top problem. So that's it. What are you thinking? Good?
Yeah.
I think so, yeah. Like drawing it out helps a lot.
Exactly. So don't forget to do that. Okay. Every single, even if it's a 2D integral, even if it's a 1D integral, I always draw them out because the integrand is most of the time it's nasty in Math 119 especially. So second question in order of importance, you showed me this, Kelly, and this is pretty good to get you thinking about what the heck is going on. Look at this. It says, suppose you have a function f of xy that is differentiable, and it means that it has both of these derivatives available at all points. Okay. It has a parabola y equals x squared as one of its level curves. Now, you're probably thinking, getting the full function f of xy is going to be complicated, but you'd be wrong, okay? Because let me tell you something. Typically, we write these f of xy's. You know how f of x, we write it as y? We do that, right? In 1D math, we do that. Well, f of xy, we write it as z. And you just saw that in the previous problem. That z is literally f of xy. Because when you isolate for z, the other side literally just has X and Y. So you see my drift here. So besides the analogy, why is this important right now? Because when you're doing level curves, what exactly is it that you're doing? Do you remember? Like, what is it that you're doing to this f of xy? Like, if you have again a mountain function like this, I like to show f of xy is like this, like an Among Us character, I guess. I don't know. But if you're doing a level curve right now, and this is the value of z, right? The height that you're in here, this is the value of z. Level curve. What does that mean? Level curve. Describe it to me.
You look from the top view.
From the top view, okay, that's a good description. But specifically, I want to know exactly what you're looking at. You're looking at a region of constant what in this case? If this is our, like the z describes our height, we're looking for a region of constant.
Said.
Yeah, constant z or constant height. So in this case, again, these level curves look like circles, right? Okay, so if we're looking for regions of constant z, they've encouraged you, I'm sure you've seen this, to replace, when we're doing level curves, you're replacing the z with what? You remember?
Hey.
Okay, okay. So you're saying f of xy needs to be a constant, okay? And so we let it be equal to k. All right, pay close attention now. So we're told that one of the level curves is y equals x squared. Huh. Could this allow us to figure out what the entire z function looks like? I'm willing to say yes, because this is now, okay, so a level curve right now, y equals x squared. Okay, and if I rearrange this, pay close attention, if I rearrange this like that, right, that is equal to 0. And tell me, okay, yeah, thanks so much, that's very useful. But do you see where I'm going with my drift here? Do you see where I'm going? Maybe you can see, maybe not.
So k is equal to 0.
K is equal to, this is the k equals to 0. So guess the function, right? Guess function. Well, I'm going to guess here that f of xy, okay, or z, however you want to write it, z is just equal to y minus x squared. Because when you do its level curves right now, you get this. And if k is equal to 0, okay, what do you get? You get 0 is equal to y minus x squared. And then y is equal to x squared. Yay. You see? So all I had to do here, okay, take this as a general rule of thumb. All I had to do, if they gave me a level curve, all I had to do to find z was to collect everybody on one side. That's all I had to do. And I've done this before in 1D math. Let me explain my drift. You've been given, like, sometimes in Math 117, they do the bisection method or the intermediate value theorem. They tell you, like, could you, like, solve something like this for us right now? And you go, okay, how do I solve this? And how you do it is, watch this. You go, okay, I'm just going to bring everybody on one side right now and equate that to 0. And I'll call this f of x. And then you work on f of x and do the bisection method. You take its derivative. Oh, sorry, that's Newton's method. You guess you do a midpoint rule. And there's a bunch of stuff like you do iterations, find the midpoint, see if the value of the function at the midpoint has changed polarity, replace. There's a lot of stuff that you do, but I want to focus on the function. That's what you call f of x, right? That's what you call f of x, because this really is a level curve, if you think about it, of the 1D function right now. It's like exactly what we did here. Exactly what we did here when I set this equal to 0. But my right-hand side here has y and x versus the right-hand side or the left-hand side here has just x. So that one obviously is f of x, and that one is f of xy. But you've done it in the past, and I just want to encourage you to think that you've done it in the past. It's not new, this trick to get the overall function, right? So if you have the level curve, again, what I'm suggesting is rearrange it so that everybody is on the same side and call this guy f of xy. You're done your work if you know this. Period. Okay? No matter what the level curve looks like, that's f of xy now that you're working on. And this parabola is its 0th level curve. There we go. Now that you've got this information, this is powerful now, okay? So now that you've got this information, how do you get what they want you to get? We want to get 2 unit vectors such that the directional derivative at 0 is equal to 0. Now, do you remember, without me showing you the formula, do you remember the directional derivative formula? Either of you?
I think it was wasn't it like the gradient of f dotted with the unit direction vector?
Dotted with a direction vector. Okay. Okay, so 1 second here, Olivia. Where's this gradient evaluated right now? Because it has to be evaluated somewhere. You remember exactly where we evaluate this guy?
Are there any points given in the question?
Exactly, the point that we are given in the question. Okay, and again, we have this gradient ready to go, and then we dot it with the direction that we want to go to. And how you put these things on the left-hand side here to keep proper notation, okay? So the point again is gonna go, I believe, let me just look at theirs. Yeah, so the point goes here, okay. No problemo. So the V goes at the bottom and the point goes here, like that, just to follow proper notation, right? That's the directional derivative. So look at you have the actual function right now and you're ready to take its gradient because you have the actual function. So again, f of xy, okay, is y minus x squared. This will make a lot of sense in a second, what we're doing, because I'm going to give you a visual too of this. But now I want to take its gradient, right? So I need, again over here, to take the dot product between these derivatives. Well, they're just going to merge with the function here, right? And then as we merge them, di x of y gives me 0. And di x of x squared here gives me, of course, negative 2x, right? So I get negative 2x, x hat. And again, if I repeat that here, I get plus, as you can see, just y hat, right? Because the di y of y is 1, and you remain with the unit vector, the other derivative being 0. So that's your gradient. Okay. Keep it like this for a sec. All right. So that's my gradient, and if I evaluate it again at the point that they want, that just means here I'm putting in 0 for x right now, and I remain with the y. So literally, this is y hat. This gradient at the point they request is y hat. Does this make any sense? Yeah, actually, let me show you. The level curve that they gave you is a parabola, they said, okay? So let's draw it in. 1 second here. Let's draw it in. It's a parabola. So, you know, if this is y equals x squared, I need to think of directions I can move here that are perpendicular right now at this point, 0, 0, to the level curve. I need to move perpendicularly to the level curve. So hold on a sec, right? Hold on a sec. If I move this way right now, that's the worst way to move, because if I zoom in, I'm pretty much moving along the level curve. Similarly, if I go, 1 second. Similarly, if I go the other way, like left, again, I need to draw very small. If I go this way, you see I'm going along the level curve. I don't want to do that, right? I want to go perpendicular. So perpendicular is indeed the y hat right now. That's going to be perpendicular to that point. There's a tangent here, right, to that parabola, and I'm perfectly perpendicular to it. That makes sense. That should be my gradient at 0, 0. Obviously, as I grow, right, as I grow the value of x, those gradients change direction, right? Like the gradient here, right, is very different right now than the gradient at 0, 0, right? But remember, we have the formula to find these vectors. If I was out there, I would just put x equal to 2. I don't know if the x is equal to 2 here, right? I'd put in the x value of 2, and then I would get an x component on my gradient. You see what I mean? And it would be pointing, the x component would be pointing a little bit to the left. You'd have the y component. So your overall vector looks somewhat like this, or again, what I've drawn here. So you have the formula to find the gradient everywhere, but we found it exactly at 0, 0, and it's just the y hat, which is amazing. This is awesome. Okay, so what do I do with this info right now? Well, they said I want to find a couple of vectors. Do I have to do this mathematically? I think you can do it in your head, but I'll do it anyways mathematically. I have to find a couple of vectors right now that have a directional derivative of 0 at that point. That's what they're asking me. So they're asking me to dot this guy, right? To dot this guy right now with some v and get 0 back. So again, they're asking me to dot y hat with some guy here that has an x component and a y component. So Vx, sorry. So Vx here, let's write it out like this. Let's write the vector in terms of Cartesian unit vectors. So he can have some x component and some y component. I'm writing it like that. It's easier for you to see. What do you observe? You observe that it cannot have an x component, or actually, sorry, you observe that it cannot have a y component rather, excusez-moi, because when I carry this dot product forwards, I get y hat dotted with x hat plus vy, y hat dotted with y hat. So, okay, this needs to be 0. Yeah, but these guys give you a 1. These guys give you a 1 right now. That's no good. That is not good, because that means you have some value here remaining behind you. Okay, so let's solve this. And this gives you a 0, obviously, here. Okay, so if that's the case, how can I make this equation 0? There's only one thing you need to do here. How can I make this equation 0? By making the y component of my vector 0. That's it. That's what you see here. I hope you can see that you're telling me you want the directional derivative to be 0, right? So when I carry out the dot product here, I remain with vy on the right. That's it. And if I want the directional derivative to be 0, then this needs to be 0. That's all I need to do right now. That means, okay, any x vector here. Thus, v can be any scalar multiple of x hat, period. Moving on, that's the solution. Does it make sense though? Do you remember what I told you? I was like, if you're on this parabola, watch how everything just makes sense. If you're on this parabola, right now, you see the tangent line at 0, 0? Like if I make it smaller, okay? If I make it smaller, give or take, the value here is the same as the value there, which means if I move this way, I'm not changing right now my value as the function. I'm not. I'm moving along the level curve. So if I'm moving along the level curve, the directional derivative is 0. I'm not changing my value. I'm on the same level curve. But if I move like this way, right? If I move there, obviously I'm not on the level curve anymore. Like there's a different level curve here, that I'm going to be at. I'm moving values now on the f of xy. I'm changing f of xy. But if I'm moving here like this horizontally, at least in the vicinity of 0, 0, I'm not changing value. I'm on the same level curve again. And that's why scalar multiples of x hat do the job here. You see what I'm talking about? They are literally moving you around, like, again, we're focusing on the 0, 0 point. Around the 0, 0 point, if you move in the x direction, no matter which way, left or right, you're still on the same level curve, that parabola, right? So that's what we're getting, the scalar multiples of x. So what would you give them for 2 vectors right now? They say give 2 vectors. What could you give them right now?
Wait, sorry, from your work before, why do you just put x equals to 0 but not y equals to 0 too?
Because, okay, so the y component needs to be 0, right? We established that. Otherwise, the directional derivative cannot be 0. If this is now 5, this breaks, okay? So we can't have a y component in our vector. So
No, like the one before, when you put in the gradient one.
Yes.
Here, yeah.
Yeah.
Why do you x equals 0 but not y?
This is y hat, right? It didn't have a y dependency, Kelly.
Oh, okay.
There's a 1 here, right? It didn't have a y dependency. So when I put in the 0, 0 point, I didn't put anything here. There's no y dependency.
Okay.
I see what confused you. So yeah, any vector that's a scalar multiple of x hat. So I'm going to say here 5x hat minus x hat. Those work. You want to say x hat and negative x hat? Those work too. So that's what you would give them. And you would see that if you take the dot product again with the gradient, you're going to get 0. Obviously, like, look, that's your gradient. It's y hat. Legit, it's y hat. So if you take the dot product with these, it's y hat dotted with x hat or 0. So no directional derivative as we desire. Fair enough? This was very cool, Kelly, because it made you think not only of how to apply the directional derivative, but also it made you think here how to reconstruct the f of xy, which is, in my opinion, something, important.
So y hat is equal to 1.
So it says, give 2 unit vectors such that the directional derivative will be 0. Any scalar multiple of x hat will give you this directional derivative. Any scalar multiple of x hat.
So I could just give like some x and like y would be always 1.
No, y hat will be always 0 for this kind of vector, okay?
Oh, okay.
Not have a y component. Now, at the same time, Kelly, they ask for which unit vectors would this guy attain the maximum value? Okay, this directional derivative would be maximum. Well, we know something about gradients. They point in the direction of maximum change. So if we want a vector that points and maximizes this, it needs to be instead a scalar multiple of the gradient. So again, if you want to maximize if you want to maximize how fast you change values here, again, the level curves are parabolas. So if you want to maximize how you change, again, values, you need to go along the direction of the gradient. We know that. Okay, we know that. They're just testing you here if you remember that. So for part A, you do this, and for part B, okay, you want any scalar multiple of the gradient. Any. Maybe the gradient itself. Any scalar multiple of di FP. That's what's going to get you the maximum value. So if di FP here, okay, so the vector that will do this is again a constant times this. Okay, and since we found that the gradient at point P is just y hat, it's any vector right now in the y hat direction, any vector. So you could give, you could give y hat, you could give negative y hat, right? All of these are valid options. You could give 5 y hat, and you'd still be growing at the maximum rate of change. Versus here, the difference was, also this was called u for them. So the difference was you don't want to change. Instead of going the maximum, you want to stay the same value. So you got to be perpendicular basically to the gradient in a way, right? Or we said here, set the directional derivative to 0 and solve for what the components of V need to be. These were the unknowns, by the way. These were the unknowns. But Vx here doesn't ever get a chance to participate because this dot product went to 0. Vy does, right? It stays behind. So we get a constraint on Vy. It's like linear algebra where you have like 3 unknowns, but only 2 equations, and you get a set of solutions. Remember, you don't get one solution in linear algebra, you get like a set. So the set here is this, any scalar multiple of x hat. That's the set. Okay? It's a line, basically. It's a line. It spans a line, this set. So you can choose the constant to be whatever the hell you want, right? As long as you're in the x hat direction, you're good to go. So that's what maximizes you, okay? And the other one is what minimizes you. What do you think now that I've done it?
I still don't understand like the u factor one. Like
The u vector?
Yeah.
Okay, one more time here, Kelly. So our goal is to make the directional derivative 0 at the point 0, 0. I've gotten the function. I hope you understood that part, right? Like how we got the f of xy. You understood that part?
Yeah.
Okay, so assuming you understood that, we got to do this operation here. This is our unknown, and maybe I won't highlight then the point P. This is our unknown. He has 2 parameters because we're in the xy plane, right? He has 2 parameters right now, an x component and a y component. This guy, we can find him by taking the gradient of your function. Obviously, we did find him, right? Here's the function. We took its gradient, and there's the gradient. Cool. But we don't want the gradient in general. We want it at a specific point. We want it at 0, 0. So I plug in to my gradient function. I plug in the point 0, 0, and that gets me only a y hat vector. Literally, just the unit vector y hat when I plug it in.
So does y hat equals to 1 then? Like if you look at it with like the 0, 1, like that? Like,
yeah, this vector is 0, 1. As a vector, yeah, it's 0, 1. I just write it in terms of unit vectors so you can see the dot products better. But it's 0, 1. That's the vector.
okay.
That's the gradient at point P, 0, 1. So you have that. Now you're going to introduce it here. And there's 2, again, unknown components to V that we need to, again, V is a 2D vector. So it has an X component and a Y component. So I go and introduce it back now over here, and you can see me. There it is. There's the gradient. Okay. There's the gradient and the unknown again components of V. So I've broken them down into some unknown X amount and some unknown Y amount over here, like two unknown amounts in each direction, right? The X hat and the Y hat. The problem though is that when you carry the dot product, the Y dotted with X vanishes. So it kills this guy with it. Like the 0 takes away this completely, okay? But when you do the Y dotted with Y, this goes to 1, so this remains. And you get a constraint on what this needs to be right now. You get a constraint that your vector V has to have a Y component of 0. It has to have a Y component of 0. That's it. You don't get a constraint on the X. The X can be whatever the hell it wants right now, Kelly. Okay? You only get a constraint on the Y. So you can't have a Y component. And that's what I wrote here. You can't have a Y component. But any X component is valid. So any constant here you put, legit, anything. So if you want to give answers, we tried 1, -1, 5, and they all work.
Oh, okay.
The other one, it's not asking the same questions. Like, where do you need to go? Where does V need to be for you to get the maximum value? Well, obviously, if you're doing a dot product, okay, when does the dot product maximize? When these are what? Perpendicular or parallel?
Perpendicular.
That's 0. Right? We said Y hat dotted with X hat gives you 0. Maximizes when you're parallel. So the only thing you can say here is that V needs to be parallel to this guy. What's this guy? He's Y hat. So V needs to be parallel to Y hat. That's all we care. V needs to be parallel to Y hat. Any constant you put here, nobody cares as long as we have this direction. And so you try constants. 1, -1, 5, they all work. They're going to get you the maximum directional derivative. Yay, nay? I lost Olivia here. Okay, let me pause the recording 1 sec while she comes back. Just tell me if you're okay with that, Kelly, while we're waiting. So I was just explaining to Kelly what the role of the gradient is. And I gave her an example with you just standing like basically here on a cliff. Like here you are, right? Maybe it's after the Math 119 midterm, hopefully not. And there's a cliff in front of you. Okay, if we wanted to ask what the gradient will tell you right now, it would tell you to kill yourself, okay? Jump on the cliff. Because that's the maximum rate of your height change right now, right? If you jump on the cliff, that's how your level curve will decrease the most, right? The maximum amount of rate of change, right? Your height here decreases very rapidly. But if you move backwards, that's where the directional derivative actually is 0. So backwards here right now makes this directional derivative 0. Forwards, okay, maximizes this. You see what I'm talking about? So I gave her an interpretation if someone was standing at the edge of a cliff, right? We'll just tell you jump off. Okay, but follow this directional derivative after the midterm, okay? Not the other one. Okay, I don't want to go overboard because I know you have a lot of things to do, but I wanted to show you one here where you have to approximate a function. Now, if you pay close attention, what you're doing when you're approximating a function legitimately is nothing more than finding an equation of a tangent plane near the points of interest here, and then moving a little bit away from those points of interest to find the value of your function. That's all you're doing here. It's a repeat, basically. You might even spot it, that it's a repeat of the tangent plane topic over here. So it's an expansion on top of this, because again, you can probably take a look at it and it looks exactly the same. Look over, you have the function point, right, over there. Delta x is, well, x minus x naught. There's the derivative, again, evaluated at x naught, y naught. And the same for the y, right? There's delta y right there, right? And there's fy evaluated at the point of interest right there. So really, you're just finding a tangent plane near the point that you're trying to approximate the function, and you move around it a little bit. That's all you're doing. So quick refresher then. Let's do one of them really quickly. The ln, I guess. Okay. So the function f of xy, maybe this is also good for Olivia because she wasn't here on that session. So ln x minus y plus 1 is your function. Okay. Olivia, can you do these two derivatives for me?
Yeah, I can try. I don't really remember how to do ln derivatives, so when there's something in the argument.
We'll do the chain rule, okay? So you will do it this way. I'll guide you on the first one. So we'll do the x derivative of the ln right now without looking at the argument. And then we will multiply by the derivative of the inside. That's how I want you to do the chain rule, even in 2D functions like this, okay?
Oh, okay. In that case, it'd be 1 over x multiplied by...
1 second. 1 over what?
Should just be 1 over x because we just assume like ln of x, and then from the inside would be just x.
When this walks in here and it sees the x, what happens?
Doesn't it just derive only the x and not anything else?
So die
multiply
x of
by
x?
1.
Yeah. And then this is 0 and that is 0 too, because they appear like constants.
Yeah.
Okay. One thing though, Olivia, is here. I want you to take a little more care on this. What you're doing is you're asking the derivative of ln. Derivative of ln, okay? Remember it like this, but really what is this? What you've put in the denominator is the argument, right? So it's really the bracket here, right, that goes into the denominator. What is the argument of ln?
So be x minus y plus 1.
Exactly. So that's what you need to get here. Okay, so it's all good. Now you know, okay? So you can apply it. I'll write the chain rule again, and you can apply it for the y. So tell me what would happen there instead.
Yeah, so it would be 1 over x minus y plus 1.
Yeah.
Multiplied by -1.
Yes. Okay, so there are our two derivatives right now. I want them, though, evaluated at the point of interest. Now I have to pick the point of interest. Okay, obviously here, what values seem to be near this point that I can evaluate f of xy with ease? Think about this for a second. Our f of xy, again, is this logarithm with x minus y plus 1. And our point of interest is here. When I'm making the decision here of where to focus the approximation, I want it to be near here, first of all. So be near here. Okay. How to choose x naught, y naught. Okay. 1, be near point of interest. So near, again, what you see there. And 2, fx naught, y naught is super easy. Okay, make a wild guess here. It's never going to be too complicated. Make a wild guess of the values near here that will make this really easy to evaluate. Make a wild guess. For for X and Y?
1 and 1.
1 and 1, right? Because if I have this, these cancel and ln of 1 is equal to 0. You see? Perfect. So you know now, okay? You know now the tricks. I guess that's an additional thing. It's not just tangent planes. You got to be careful where you're going to focus the approximation, right? All right. Now, what else did I want to ask you here? Oh, yeah. What if I tried, again, because it's ln x minus y plus 1, what if I tried here, like, to focus this approximation at, let's say, 2 minus 2? Why is that not good? That's easy to evaluate. Why is that a problem? What do you girls think?
Is it because like the difference between 2 and 1.1 and 0.9 would be really big?
Yes. So this is bad. You can do it, but the approximation is going to be trash. Okay? So that's what I'm saying. First, look near here, and then look for points, again, that will make the function evaluate like in a snap, right? All right, we understand that. So we got the derivatives. Now I got to evaluate them where I chose my actual points to be. And I'm going to do the approximation. And that is at 1, 1. Nice. Okay, so this one here is just 1 over 1 minus 1 plus 1, or just, as you can see here, 1. The other one, same point again, we chose 1 and 1 to do our approximation. So the other one again here is going to be 1 over 1 minus 1 plus 1. Don't forget the negative 1 on the top. So we overall get negative 1 instead from this. Okay. So we got the value of the derivatives. Okay. Now what I have to do is fill in the equation of the plane. One last thing I need to do, of course, is evaluate the function at the point of interest. Okay. The function was, again, ln x minus y plus 1. So ln 1 minus 1 plus 1. We said that's going to give you ln of 0. Sorry, ln of 1. Ln of 1. Yikes. And then this is just 0. Awesome. So you put it all together now. Remember, the equation of that plane is going to be x minus x naught, okay, times the derivative with respect to x evaluated at the point that you chose to do the approximation. Then you do plus y minus y naught, same deal with the y, evaluate the derivative there at the point you chose to do the approximation, and then add the value of the function there at the point that you chose to do the approximation again. You can fill all these in right now. You see them. The point of interest, okay, all these are 1s. You chose to do the point of interest at 1, 1. All these are 1s right now. Okay, so you go to the next step. You got x minus 1, fx at 1, 1, plus y minus 1, fy 1, 1, plus f1, 1. And now you bring in, of course, the values from here, right? You bring in the values from these guys to fill these. These were 1, negative 1, and 0. You see, I'm just plugging and chugging. So I got here x minus 1 plus, well, that's going to be 1 minus y plus 0. And then I fine tune this a little bit, and I get myself, let's see, x minus y. These go away. That's it. That's the equation of my plane. So, right. So if I want right now to evaluate, again, what the value of my function is going to be. So now I want P, Well, at 1.1 and 0.9, right? That's what the whole goal was. So we have that plane, it's tangent at 1, 1, and we just want to find what the value of the plane is nearby. So you just plug the values in and evaluate. Do you see? Well, I have to be careful though, 1 second, because I have to be a little bit careful. 1.1 minus 0.9, that's 0.2. Let me just check, because sometimes I make silly mistakes. Let me just check to make sure no silly mistakes were made. This is an approximation question, and it was probably, I'll be looking for it for a sec. Let me just pause. So all is good, right? The goal was to choose a point that's near where we want over here. That's again, that's the first thing, be near. And the second thing is choose it so that it makes this function really easy to evaluate there. That's the whole goal. You don't have to use your calculator. That's what you want to be doing here. So obviously 1 and 1 worked here. So I needed all the partials. I needed fx, I needed fy, and then I needed to evaluate them wherever I chose to do the approximation. And that's what I did for both of them. Then I needed to evaluate the function where I chose to do the approximation. That's what I did here. Then I filled in the recipe that I've told you before for finding the equation of a tangent plane to an f of xy. Filled it in, got myself the equation of the plane, and then I wanted to evaluate it at these points. Now, the further away you go, the trashier this will work, okay? If you were to evaluate it right now at 2 and 2, no, not good. You're gonna see. Let me show you what I mean. Do this right now. Ln, so evaluate the function at 1.1 and 0.9. So go ahead and do ln of 1.1 minus 0.9 plus 1. Do it in your calculator. What do we get? We get 1.1 minus 0.9 plus 1. And then we take the logarithm of 1.2 basically. Okay, so that is 0.18. Do you see? Do you see how close it is? It's a good approximation, right? But, okay, what if I went to do it, like I said, at 2 and 2 right now? You'd get here 2 minus 2 or 0. And then versus the actual function, look at this one now, just to see how trashy it will become. Ln of 2 minus 2. Actually, wait a minute. This is a coincidence or what? It might be a coincidence. Okay, I take it back. That's a coincidence. That's a coincidence. And it always happens when I want to prove a point. It's a coincidence because both of these converge to 0. You'll get ln of 1, obviously, which is 0, which means perfect agreement. But that's not because the approximation is good. It's because they both of these functions meet at 0. They both meet at 0. These are equal, and these are equal. They will just evaluate to 0. It's just a coincidence. Because let me show you what happens, for example, if you go to, let's say 3 and 3, okay? Or, yeah, 3 and 3. You see, they will agree for every ordered pair here. They will actually agree. This will get you 0, and this will get you 0. Interesting. So you have to make them a little bit different. Okay. So I'm going to choose here 2 and 0. Okay, that's good. So let's do that. Just to show you that it doesn't work well in further away points. Okay. So 2 and 0 would get you 2 minus 0, or just 2. This guy would get you 2 minus 0 plus 1, or ln of 3. And ln of 3 is 1.09, or 1.1. Do you see how much worse this is right now versus this? Look at the inaccuracy. If you wanted to build something using the model on the left, you're screwed right now. Right? It's almost double the value than what it should be. Versus here, it's like 80% the value, let's say 90% the value of what it should be. Anyways, it's a coincidence, by the way, for ordered pairs, these functions agree to give you 0. It's a coincidence. And I noticed it. And of course, it had to be the example that I used. Of course, but the further away you move from where you made the approximation, so 1 and 1, the worse these approximations are going to become. Anyways, so pick them with care. Pick where you want to do the approximation with care. All you're doing is finding a tangent plane again and evaluating it for a nearby point. Okay, are you good? That's all I had to show you today. Okay, I don't want to keep more of your time. Unless you have your own questions that you want to ask me. I don't mind. It's whatever. Kelly, Olivia?
I think I'm good. Is differential means like derivative?
Differential is this guy over here. Like you see these delta x, these delta x's and delta y's. These are usually called differentials if they are. These are differentials. Okay.
Oh, okay.
So exactly these. But again, using differentials, it just means using, again, it's a jargon for approximating using a tangent plane. So use differentials. I basically derived here how you can use differentials to get the approximation, which is a tangent plane. Like when I got to the end of the derivation, I am showing you the equation of a tangent plane again. That's what I'm saying. Like differentials, using differential for approximations leads you to doing the tangent plane technique. So just do the tangent plane. Like honestly, just hear me out. Just do tangent planes if you encounter a problem like this. But pick the point carefully. That's it. All there is to it. Any other questions?
No, that's it.
All right. Let's call it then here. If you're good, Olivia, I'll stop the recording. We're all good.
Do you know of any other like sources for more in-depth practice problems? Like for example, they give us practice problems in like on Learn, but I think some of them are not super like covering a lot.
Again, my own repository, but the thing is, Olivia, they don't include differential equations anymore in the curriculum, or if they do, it's packed in a subject later in the term. I don't know. You guys are going to let me know.
I think it'll probably be later.
Yeah, if they do differential equations, just let me know. They did them here in a way where each week they build up a little bit on differential equations versus I think what you're going to do is you're going to do it all at once in one chapter in a particular week. That's the difference. So they spread them.
What's like the quote unquote second half of 119 cover?
Taylor series. Okay. What else is there? Are you going to do power series? Probably power series. Power series and Taylor series are the same thing.
Oh, okay. Because Taylor series we've done in 1 week, to my knowledge.
What else do we have here? Like find a polynomial of degree 4. What are these questions? What's the topic here? Fourth order Taylor polynomial. So Taylor's inequality. Oh yeah, you're gonna have to suffer finding the error of Taylor series. Linear approximation. Linear approximation is a Taylor polynomial of order 1. That's all there is to it. You'll see me do that here again. I'm just doing a Taylor series of order 1. Usually just an equation of a line. Okay, and then you do, okay, Maclaurin refers to a Taylor series centered at 0. A lot of Taylor series stuff. Still Taylor series. You're going to do integrals using Taylor series, which is cool. It shows you a practical problem of why they're important. because integrals like this, you can't solve, right? You know, you can't like, I guess here, yeah. I hope they show you an example like where you have an integral that's not solvable if you don't approximate it as a Taylor series. That's a good one. And then you have a little bit on series. Okay, are you going all the way into series? Let's see. Still Taylor stuff. Yes, you are. Okay. All right, so a little bit of Math 128 here. You're gonna have to learn how to make these series converge or diverge. Like you're gonna learn a bunch of tests that you're gonna be applying to these to see if they converge or diverge. This is the most annoying thing about Math 128. Not hard though, not really hard. Okay, and then assignment 9, radius of convergence, interval of convergence. Okay, so all Math 128 stuff here. I'm just looking. So it looks, Olivia, like the next topics you're going to do a lot of stuff on Taylor series, a lot of stuff on power series. Power series should be introduced first and then Taylor series, honestly. That's what makes sense to do. Then you're going to do convergence tests. That's what they're called. I have them summarized. If you're interested, I'm going to give you a cheat sheet. Don't worry. Where did I put them? Every time I'm looking for something. There. So all of these you're going to come across, like they're just tests that you apply to those series that you saw to see if they converge or not. Okay. You're going to be asked about this. And then the last bit, if you saw, was on the radius of convergence and interval of convergence of series. So in summary, power series, Taylor series, convergence tests. That's what's coming. It's all on series, the later part, it seems. All of it. You might do approximation methods right after the midterm. You should, because that was part of the curriculum back then too. Like right here, Newton's method, for example. So you're going to do the intermediate value theorem, bisection, and Newton's method. You should. I don't know. I don't think they've kicked this out of the curriculum, but we'll see. So approximation techniques, Taylor series, power series, convergence tests, and some stuff on radius and interval of convergence. That's the topics that remain. And I would say they're a lot easier than what you're doing right now. Triple integrals are not easy, girls. Versus this stuff is actually pretty straightforward once you get to understand it. They have a method, a methodology.
Wait,
okay.
for the term, I asked the professor and she told me like if we practice for the practice sets, we'll be okay. So do you think they'll be as hard as the ones she showed us?
The ones I showed you, they are from practice tests from spring 2020.
Oh, okay.
The quarantine spring, okay? They're from then. So they are from Math 119, literally. I only just have one set of problems. You're more than welcome. Like you were sending me stuff. I will add to the folders. Eventually, I want to make this into how Math 117 looks. You see, I have all the topics here arranged and questions on each topic. That's how I want to make Math 119 too. I'd love that. But that's after I gain a little bit more insight of what the course actually covers, right? Because I'm not 100% sure what they go to. They're all over the place sometimes. So once you girls feed me with more assignment sets, that's how the Math 119 folder will look, okay? But for now, I just have one roll of assignments from spring 2020 to guide me. So I only ran this course once, okay? Any other questions?
No.
No? Olivia?
I think I'm good. I think I just need to get more sleep before the midterm.
Perfect. Well, you do that, all right? And I'll catch you tomorrow. Then let me just stop the recording here.